Welcome to Chapter 12. This is the first chapter in the book that focuses on integration, definite integrals and indefinite integrals. This chapter is mostly focused on building intuition and visualization. And in the next chapter, we will begin to get a little bit more rigorous about defining exactly how integrals work and what they mean, how to interpret them, and so on. Okay, and so we begin with exercise 1, which is focused on cumulative summation. The cumulative sum is basically just the running sum of a vector of numbers, of a set of numbers. Cumulative summation is the building block for basically all of integration, definite and indefinite integrals. And so the goal of this exercise is really just to make sure that you really understand what cumulative sum means. So what I want you to do is write Python code to calculate the cumulative sum of the numbers 1 through 10, the integers 1 through 10. But here's the thing. Now, you can just use numpy.cumSum for cumulative sum. But that would be too easy, right? The goal of this exercise is not just to implement the cumulative sum by calling some function that someone else wrote, but instead, I want you to write your own code to implement the cumulative sum directly. And then, of course, you can also use numpy.cumSum to make sure that your code is accurate. But the purpose is to make sure that you really understand how the cumulative sum works by writing it yourself without using this function. Okay, so I don't know how many distinct ways to implement the cumulative sum in Python there are. I am going to switch to code and show you 3 ways, and maybe you have come up with some other ways, which is also great. As long as you get the correct answer, it doesn't matter how you implement it. So here is the vector of integers that goes from 1 to 10. Remember that numpy.arange has an inclusive lower bound, but an exclusive upper bound. So in fact, this is going to give us the numbers, the integers, 1 through 10. I'll just show you that real quick. So exclusive upper bound, inclusive lower bound here. Okay, anyway, here I am initializing 2 of the cumulative sum options or little algorithms. Here is one option. So I'm looping over all of the numbers, and I'm saying that each element in the cumulative sum is equal to the sum of all the numbers from the beginning up until the current element. Okay, so that's one way to implement it. This is another way to implement it where I initialize the first value, the first element in the cumulative sum to equal exactly the first element in the set of numbers. So that's actually not summing anything yet. That's just saying that the first element here equals the first element here. And then what I'm doing in this for loop is summing the current element of the numbers, so element I, and the previous element of the cumulative sum. Okay, so now I'm not summing over all the numbers here, but instead I'm just adding the previous cumulative sum value to the current value in the vector of numbers. And then finally, option 3 is to implement this as list comprehension. So here I have a single line for loop. So this is the for loop. And then I'm just summing up all the numbers from the beginning up to the current index here. And here I'm using the built-in Python base function sum instead of numpy.sum. Now, these 3 different options are fundamentally not different from each other. They're all implementing exactly the same algorithm. So why do I show 3 different options? Well, it's really important that you understand exactly how the cumulative sum works and what it means. And therefore, seeing it written out in a few different ways is really going to help make sure that everyone understands what this cumulative sum means. Okay, so then I'm printing out each of these 3, and now here I'm using numpy.cumSum. If the universe works the way I think it does, then all 4 of these printed options are going to look identical. Well, okay, maybe not identical with some formatting issues, but that doesn't matter. That's not relevant. Yeah, you can see the numbers are the same. The cumulative sums are the same. Needless to say, in practice, you should always use numpy.cumsum. Doesn't really make sense to write out your own code for cumulative summation, but when you are learning about cumulative summation and integrals and integral approximations, I think it's important to write out these algorithms at least once to make sure you really understand how they work. And then in the future, in applications, save yourself some time and coding and just use the NumPy implementation. Welcome to exercise 2 of chapter 12. The goal of this exercise is to create a Python function that implements the derivative and the integral of some input values, but this is not the analytic derivative or the analytic integral using pure math calculations. Instead, this is going to be the numerical approximations of the derivative and then the numerical approximation of the integral, but it's going to be the integral of the derivative, not the integral of the original function that you input into the Python function. The idea, the goal of this exercise is that we are going to confirm and explore the fundamental theorem of calculus part 1, which basically says that integration and differentiation are like inverse operations of each other. So that means that if you start with some math function, if you take the derivative of that function and then you integrate the derivative, you should get back the original function. Okay, so that is the FTC one. And yeah, we're going to write a Python function that implements the approximation of this. Okay, so here's what you want to do. Write a Python function that takes a vector of x-axis values and corresponding y-axis values that come from some function that we can define. Okay, so those are the two inputs to the Python function. And there's also two outputs from the Python function. So we want to output the numerical approximation of the derivative using numpy.diff. Now, you know how to do that from previous chapters. And also, we want to output the integral of that derivative, okay? And this is what's new here in this chapter. And the integral, the numerical approximation of the integral, is based on equation 12.2. I will scroll up in a moment and show you that equation. So here is equation 12.2. This says that the integral is the cumulative sum. Of course, you know all about the cumulative sum from the previous exercise of the function values times delta x. Okay, now in this exercise for this Python function, this f of x here is going to be the numerical derivative of the input values. Okay, so this is going to be the cumulative sum of the derivative that you calculate times delta x. Now, once you've implemented that calculation of the derivative and its integral, you need to normalize the integral using a constant of integration. As I write here, I haven't yet introduced the concept of normalizing an integral. You will learn all about that in the next few chapters. But for now, just follow the following instructions to write this algorithm. The first step is to find the array index at which x is closest to 0. So basically, let me start by telling you about the end result here. The end result is this that you see here, this constraint here. So we want that the integral of the derivative at x equals 0 has the same numerical value as the original function at x equals 0. So this is the original math function. This is y equals f of x that you input into the Python function. And the goal of the normalization is to make sure that the integral of the derivative at x equals 0 equals the function value at 0. There is a theoretical motivation for specifying this constraint, which I will discuss in the future. For now, suffice it to say that this is the goal. Okay, so how do you get this? So find where x equals 0 and then you subtract the value of the integral at x equals 0 from the entire integral. So that is basically ensuring that this value here equals 0. So the left-hand side of this equation will equal 0, and then you find the value of the original function at x equals 0 and add that back onto the numerical approximation of the integral. Okay, and then altogether those three steps will satisfy this constraint over here. Okay, when you've written your function, confirm its accuracy by reproducing the table below. Okay, so here's the table. We have the values of x, the values of f of x. This is from the original function. And you can see, I didn't write out the actual function here, but I think you can see that the function is simply x squared. Okay, so we square all of these values and we get these values. This is the empirical derivative that we compute inside the function, the Python function, and this is the integral of the derivative. Now, according to the fundamental theorem of calculus, part 1, this column here, which I call IDF for the integral of the derivative of the function, this column here should exactly equal the original function over here. Not a numerical approximation, but literally exactly. That is what the theory of calculus tells us. Now, it's obviously the case that these two columns are not equal. They are, only at value 0 are they actually equal. Okay. Why is that the case? That's basically due to the accumulation of numerical errors that arise from implementing this as discretized values. I will have more to say about that when I show you the code. So here we are in Python. Here you can see the function, which I call deriv and integral. It takes two inputs, the values of x and the values of y equals f of x. So the function evaluated for these specific values of x. Here I compute the numerical approximation of the derivative. Now there's nothing really new. Here in this code, you've already seen this in previous chapters. This is a little bit new. I'm adding one more value, and that's just to make sure that the variable df has the same number of elements as the input function values, instead of having one element fewer because of this numpy.diff function. Okay, and then here is where we compute the discrete integral, or the numerical approximation of the integral. Here I'm calculating the cumulative sum, you know all about that from the previous exercise, times dx. So we need to have this scalar in this function. Okay, and now again, this is not the cumulative summation of the function input, the mathematical function input. Instead, it's the cumulative sum of the derivative approximation that I calculated up here. And here's where I normalize the function. So basically, I'm finding the index at which this vector x is closest to 0. So the absolute value of x is basically going to give us a v-shaped function for negative values going up, positive values going up, and the value closest to 0 is going to be the minimum of this absolute value of x. Okay, and then I subtract the value of x from the integral, and then I add back to the integral the value at x equals 0 coming from the original mathematical function that we inputted into this Python function. Okay, pretty straightforward. And then here I just return the derivative and the integral of the derivative. All right, and then here is where I create that table. And yeah, once you have, so here's the function, the x-axis values, and here is the calling this function and getting the output. And then this is just creating the table. Yeah, okay, so this column and this column here should match exactly identically, which they clearly don't. One thing I would like to just point out before going on to the next exercise, where we will explore this issue in more detail, is that just by changing the number of x-axis points, we can actually make that match closer. So instead of 6 values between -1 and 4, I'm going to rerun this function and recreate this table using 60 values. Literally nothing is changing in the code except for the number of numbers between -1 and 4, which means the resolution of the function evaluation. Okay, so that means that basically delta x is now smaller. And now again, you can see this table is much longer, but now we want to compare this fourth column and this second column. And we see, okay, so it's still not exactly correct, but they are a little bit closer than they were before, right? So the end result here was 16 for the true values and 16.6 for the approximation. So it's certainly closer. Now I'm going to try it again. How about 260? Again, I'm changing nothing in the code. I'm certainly not changing the what's happening inside the function here. The only thing that I'm changing is the resolution here, increasing the resolution. And as we increase the resolution, the accuracy of the numerical approximation increases. That is an important theme that comes up over and over again throughout this book and basically everywhere in applied calculus and lots of areas in mathematics. Now for exercise 3, in which you will use the Python function that you created in the previous exercise to visualize some functions and the approximation of the fundamental theorem of calculus, part 1. Okay, so if you use the function x squared with 27 x-axis values linearly spaced between -1 and 4, then you will reproduce figure 12.7. Here is figure 12.7. This is the original function. This is the numerical approximation of the derivative. And here we have the reconstruction of the original function as the integral or the numerical approximation of the integral of the derivative. Okay, so this function, all the values in this function come from the Python function that we created in the previous exercise. So that's the goal here. And then you can also explore how the resolution that you specify changes the visual appearance of the mapping between the original function and the approximation. Again, the fundamental theorem of calculus tells us that this black line and these triangles should be exactly identical. They should overlap perfectly. The fact that they don't is basically just telling us a little bit about the accumulation of errors in digital computers. When you have the matplotlib code working, then you can explore some other functions. Here I just give 2 suggestions. You can also make up your own functions. It's great. I definitely encourage that. These are the 2 functions that I have also implemented in the code. So here we have our function x squared using the x-axis values that I specified. And here's where I get the derivative and the integral from this Python function that I wrote for the previous exercise. And this is just visualization. I think there's not a whole lot to say here. So this is the first panel where I'm showing the function. This is the second panel where I'm plotting the derivative. Now, in this case, I'm only plotting the first n-1 points of the derivative. And then here is for the integral. And remember, this is the integral of the derivative, not the integral of the original function. Okay, so yeah, this just reproduces the figure in the book. Okay, so now what I want to try is reducing this. So how about 7? Remember, in the previous exercise, we created that table with n equals 6 points. So here is with 7 points. And what you will see is that the discrepancy is really terrible. These two don't seem to overlap at all. Okay, really bad. And now I'm going to go up to, how about 777 points like this? So almost 800 points. And now we can look at this mapping, and it's going to be completely, okay, you don't really see anything. How about we make this a red line? So we have the function as a black line, and the integral, the approximation of the integral of the approximation of the derivative. So this is like a lot of numerical approximations that we are doing here. Uh, the red line and the black line should be overlapping perfectly, and you see that looks really good. Again, I haven't changed anything in the code. I haven't changed any algorithms, any implementational details. The only thing that I changed to get these two lines to look really, really close to each other versus really far apart from each other is increasing the resolution of the x-axis. Okay, so now I'll run this again with the lines with this low resolution. And here, all of a sudden, the lines don't seem to match very closely. The goal of exercise 4 is to write code to produce this figure. So what are we looking at here? Well, we see there is a math function drawn here with a black line and the dark gray squares. That is the function x squared minus 0.5. So it's just x squared and then shifted down on the y-axis by 0.5. And then we see bars, these gray, light gray rectangles that are drawn in. And now the idea is that the area between this math function and the x-axis, or the y equals 0 line, that is approximately equal to the sum of all of the approximating bars here. Okay, so how do we define these bars and how do we discretize the function? So it's points between, so x-axis values between minus 0.5 and 1.1. And we want to set delta x equal to 0.2. That is going to give us 9 bars. You can count 9 bars here. This one is very thin. It's very close to 0. Where the height of the bar is determined by the function value at each of these x-axis points. Okay, so draw this function, sum all of the areas of all of these bars, and then that's going to give us a total area of 0.666. Just happened to work out that way, I promise. Now, you can see that some of these bars are negative and some of these bars are positive. That is a distinction between net area and total area. I have not introduced those terms in this chapter, except for right now. I'm going to talk about what those mean and how to calculate net versus total area in the next chapter and also in the next few chapters. For now, you can just take the absolute value of the function. So to calculate the area of this bar, you multiply delta x, that's the width of each rectangle, times the function value, and that might be negative, it might be positive. Then you take the absolute value of that area estimation, and then you sum that onto a running total of the area approximation of the function. Here I have a Python function for this math function. Here I am defining the width, delta x, and here is the resolution, so the x-axis values. So minus 0.5 to 1. Remember that this is an exclusive upper bound, so we need to add on a little bit extra in order to get up to 1.1. Okay, and then in steps of dx. Here I define the function, and here I plot the function. So far, so good. This is just basic visualization. There's no calculus here yet. Okay, here's where we're starting to get into calculus. So I initialize the area approximation to be 0, and now I'm looping over all the values in x. Here is where I'm calculating the height of the bar, so that is f of x times d of x, and this gives me the area of the rectangle, right? So it's the width times the height. And then, as I mentioned, you're going to get negative values in here. So you take the absolute value of those bars and then sum them all up together. So this estimate of the area is increasing with each element in xi, or in x. And here's where I draw the rectangle. So you can see these are the x coordinates and these are the y coordinates. I define the x coordinates to be each of the x-axis values minus 1/2 of dx, so 1/2 of the resolution, and then this particular x-axis value plus 1/2 of dx. So this together is going to guarantee that we get the rectangle drawn at the center point of the x-axis coordinate with equal size on both sides of that x-axis point. And then, of course, the height of the bar is the same for both the left and the right side, so it's the function value. Okay, and then, then I'm making the plots there. Great, so here we see that figure, and again, this is the approximation of the area between this function and the y equals 0 line. Now, we are going to continue exploring that approximation and the accuracy of that approximation as it relates to delta x in the next exercise. The goal of exercise 5 is to continue exploring the approximation that we developed in the previous exercise. So the approximation of the area between a function x squared minus 0.5 and the y equals 0 line. So there's two parts to this exercise. The first part is a little bit more kind of exploration, intuition based. And then in the next part of the exercise, we are going to investigate the accuracy of the approximation a little bit more rigorously and systematically. Okay, so first what I want you to do is go back to the previous exercise, the code for the previous exercise. Remember that produced this figure here. And basically just explore different values of delta x and see how the estimation of the area changes. So you don't need to do this like really in depth. Just play around, try a couple of different parameters, a couple of different values, and then we will come back and talk about the more kind of systematic investigation in this exercise. So here was the figure from the previous exercise. And now what I would like you to notice is that with these rectangles, with these bars, we sometimes are overestimating the area, right? This little triangle here from this rectangle is outside the area. This is an overestimation. It's an error. It's an approximation error. Whereas other times we have here, this white triangle here, this is empty. There really are function values here. So this area is being missed by the approximation. So it's an error of underestimating the area. Now, maybe you have the kind of visual intuition that the overestimates and the underestimates are kind of balancing each other out. So in the end, it's not a big deal. That is true to some extent, but whether we are overestimating or underestimating depends on a variety of factors, including the characteristics of the function and also the exact ways that we approximate. I will have more to say about this in the next chapter, but now I want you to just have some visual intuition that with a limited resolution, we are going to be sometimes overestimating, sometimes underestimating. Okay, so let's try this again. And now I'm going to set the resolution to be 0.05 instead of 0.2. So what this means is that we're just going to have more bars, right? There's going to be more x-axis values, and dx is smaller, which means each of these bars is going to be thinner. So now you see that here you can see these bars are all thinner, and now there's still going to be some overestimations and underestimations. Maybe I'll turn off this. I'm going to get rid of these squares here just to make the plot a little bit easier to see. Okay, so you see we still have overestimations and underestimations, so we're still getting approximation errors, but those approximation errors are smaller, and the area also decreased. So that tells us that although with delta x equals 0.2, we had some overestimates and some underestimates. Altogether, the global impact was to overestimate this function. Again, that is not trivially always the case. Sometimes we'll have a global underestimate The sign of the error depends on a variety of factors. Okay, but certainly the area decreased. And I think you have the intuition that the smaller we make delta x, the more accurate area is going to be. And that leads me to the next part of this exercise. So what you want to do is calculate the exact area under that function or between that function and the y equals 0 line using this SymPy code. So sim.integrate, here I have sim.abs for absolute value of sx squared minus 0.5. So this is the first input into the integrate function. This is the absolute value of the function x squared minus 0.5. And this variable sx, that's just a symbolic variable. You can also use variable x if you like. So that's the first input. The second input is a tuple. It's a 3-element tuple with sx minus 0.5 and 1. These correspond to the bounds. Now for the next part of the exercise, where we are going to explore the accuracy of this approximation as delta x decreases, okay, as we get more and more bars. Now, the true area between that function and the y equals 0 line is somewhere around 0.573. I calculated that in SymPy using this code. So we have sim.integrate, and then we have two inputs into this function. The first input is sim.abs for absolute value of sx squared minus 0.5, and sx is just some symbolic variable. So this is inputting the function with the absolute value. The reason for this I will explain in more detail in the next chapter. But for now, suffice it to say that this is the way to calculate the exact integral of the function. And then here's the second input into this sim.integrate function. It's a tuple. It has 3 elements. The first element is sx, which is again the symbolic variable. And then the other 2 numbers correspond to the bounds of integration. So we want to know the area of this function for this variable from 0.5 minus 0.5 to 1.1. Okay, so that gives you the exact value. And now what I want you to do is copy the code from the previous exercise, from exercise 4, and put that into a for loop in which you systematically vary delta x between 0.001 and 0.5. Now, when you paste the code from the previous exercise into the for loop for this exercise, you can exclude the graphing. We don't need to draw lots and lots, I don't know how many points here. You don't need to draw like 25 different plots. Just the code for calculating the area from the previous exercise using a range of x-axis values from 0.001 to 5. Now, I specified the range or the values between these two numbers to be logarithmically spaced, and that gives a log-spaced x-axis that you see here, okay? So what you see here is on the y-axis, it's the area between the function curve and the y equals 0 line. So that is the definite integral. Here I have the approximations from the NumPy calculations. And then here, the dashed line is the exact value that we get from SymPy using the code that I just explained. I will have a couple of remarks about this plot, which I will get to after showing you the code. So here I'm calculating the exact area using SymPy, and then here I'm just printing out the area from SymPy, and this is the NumPy approximation from the previous exercise. Now, this does not say 0.666 because I changed delta x here. So we can go back to, let me see, where was this? It was here. I'm going to set this back to 0.2 just to make sure it's a little bit cleaner and more consistent with the book. Okay, so this is from from exercise 4. And then here we have the exact area in SymPy, and this was our numerical approximation. Okay, here I am setting up this systematic investigation. This should say point 1 here. Here I have the values of dx going from 0.001 to zero point 0.5 in 20 steps. And here I'm initializing the approximation values. Okay, and then, yeah, here I'm just looping over all of the different x-axis resolutions. So this here is code copied from the previous exercise, from exercise 4. And you can see I've excluded all of the visualization code because we don't want that here. Okay, and then here I'm making the plot that I showed in the book. So a couple of remarks here. One is the most obvious thing, which is that as you increase the x-axis resolution, which means decreasing the value of delta x, so making the bars be thinner and thinner and thinner, the approximation starts out really terrible, and then it gets much, much better in the sense of being much more accurate, closer to the exact value. In fact, when delta x gets so small that it's basically just some tiny, tiny number above 0, so as the limit of delta x goes to 0, then this approximation becomes the exact definite integral, which is what SymPy is calculating. Okay, so that is one thing to remark. Another thing to remark is that the decrease in the area, which is the accuracy of the function, it's not really smooth. I mean, it's going down in general, but you can see like here, the approximation actually got worse for this one step here, even though the x-axis, the delta x is smaller here than it is here. So, and here it also looks like it got a little bit worse before getting better. Maybe even here it's a little higher. But anyway, the reason why this happens is that in general, discretizing the x-axis to finer and finer increments, finer and finer segments, does indeed improve the approximation accuracy. But how well it improves from one value to the next depends on the nature of the function and on the bounds, in particular, where these boxes are drawn relative to how the function is changing. And that is related to this issue of where we get over approximations and where we get under approximations.